Alright guys, so this is just going to be a quick video on how to do the basic, or actually not basic, the additional trig identities. And I'm only just going to show and prove all of them. I'm not going to do any of the problems, but I'll derive all of them, so hopefully you'll be able to see how it works. Alright, let's do it. Okay, so starting off with this rectangle looking thing, just notice how it's a rectangle from here. We got the 4 right angles, or actually really only 2 opposite right angles. And from here we're just going to do a little bit of labeling. I'm going to first label all the angles. So we know this right triangle right here, so this is going to be 90 minus alpha. And then additionally we know that this is right here, we know that this angle is 90, so it's going to be 90 minus alpha plus beta. And then up here, actually we'll go to this angle right here. This angle will be alpha, and we can check this as we know 90 plus 90 minus alpha plus this mystery angle, I'll just say x, and we know that equals to 180. So if these two cancel out, we know 0 is equal to negative alpha plus x, so that means x must be alpha. So that's pretty easy right there. So we know that angle is alpha. Alright, moving on. So that means we also know that this is also 90 minus alpha. And then from here, we know that we have this right triangle. So we can find this angle up here, which is going to be 90 minus beta. That means this angle, let's just say it's y for now. That means we know that y plus 90 minus beta plus 90 minus alpha equals 180. So then we can cancel out the 90 and the 180. So we know that y minus beta minus alpha equals 0. So we know y is equal to alpha plus beta. So we're just going to insert that there, and we're going to erase everything up here just to give ourselves some more room. So we know it's alpha plus beta. And that should make sense, because if we add all these together, we should get 180. And this works with this one too, these two angles, because we know that these two must add up to 180, so that's great. All right, from here we're going to start labeling some sides. We'll have, let's just start with, since we don't want to do A, B, we'll do A, B, C, D, E, F, G, H, I, and J. Oh, that should be a lowercase. And let's see, did I miss any sides? No. All right, so let's just get right into it. So if we look at this internal triangle, we can tell that the hypotenuse is 1, obviously. So we know it's on the unit circle. We know it's some sort of unit circle type of triangle. So we can easily solve for f in this case. So if we just erase this part, I'm going to go over here, and f is going to equal the sine, or yeah, sine, because it's the opposite of beta. It's going to equal sine beta. Or actually, f over 1 is going to equal sine beta. But as we know, anything divided by 1 is just itself. So that works out pretty well. And we're going to insert that right there. And we can use the exact same logic for d. And that's always going to give us cosine of beta. And with these two, we can solve for the entire rectangle. All the sides we can find in terms of these two angles, which is great. So from here, we'll go look at E. So we know that E, if we take sine of alpha, we know sine alpha, in this case, if we use this alpha, which is the same as all the other alphas on the page, I just want to make that clear. If we take sine alpha, we know that's equal to E over cosine beta, because we have it up here. So if we solve for E, we get E equals sine alpha cosine beta, which is great. And we will plug that in. So we'll erase this, and we'll put this in. So we get sine alpha cosine beta. Great. And for C, we can use the same logic. So we get that cosine of alpha is equal to C over cosine beta. So if we just bring this over to that side, we're going to get C equals cosine alpha cosine beta. And this will all make sense in a second. So let's just erase this C, and then we'll get cosine alpha cosine beta. All right, from here, let's move up to G. So we can use the same logic here. So we have cosine of alpha is going to be adjacent and hypotenuse. So that's going to equal g over sine beta. And we can just move some stuff around. So we get sine beta, cosine alpha. Or actually, this will make more sense if I do it this way, but it doesn't matter at all because multiplication doesn't really depend on order. Equals g, and we'll just plug that in here. So that makes it easy. So cosine alpha sine beta. And now I'm just going to erase this to make some room, but we can solve for h in the exact same way. So we know that h over sine beta is going to equal the sine of alpha. And then we can obviously just reorganize, so sine alpha, sine beta. Nice, and we'll just plug that in. And then moving on, we'll solve for I. I'm just going to erase this to make some more space. So I is going to use this side of the triangle. So if we start from here, we know that I over 1 is equal to cosine of alpha plus beta. So we'll just plug that in. That seems a pretty easy one. So this is going to be cosine alpha plus beta. And we're just going to erase this to make some more room. And then j in this case is really nice and easy. It will be, if we have j over 1, it's equal to sine alpha plus beta. So we can just plug that in to get sine alpha plus beta. All right, from here, the most important thing to know is that this is a rectangle. So that means opposite sides must be equal. So this will give us our first identity. So we'll take this side and set it equal to this side. So basically we're gonna get sine of alpha plus beta, all in parentheses, is equal to sine alpha cosine beta plus cosine alpha sine beta. And we'll notice from here that this makes a sine-wich because the signs are on the outside. Sine-wich. And I'm going to erase this to make some more room. And just notice how the sines are on the outside and the cosines are on the inside. And when this is minus, if this is a minus, the inside will be minus as well. Now, moving on, we'll use cosine. So it looks from here that this side has to be equal to this green side. So we have cosine alpha times cosine beta is equal to cosine of alpha plus beta plus sine alpha sine beta. And if we just move this to the other side, we're going to get our second summation formula, which is cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And as you can see, this one has the two functions next to each other, and cosine is first. So you can just remember this as cosines stay together. And notice how we have a plus in here, but it's a minus in here. This is important to note because if this was a minus in here, it would be a plus in there. So cosine is one of those where the inside is actually going to be the opposite of the identity. All right, moving on. So we're just going to formalize these. If we just take this, we're going to write this out as our sine-wich, which is going to be sine alpha. Oops, already messed it up. Sine alpha cosine beta. So sine of the first one times cosine of the second one plus or minus. So we're going to match this plus or minus of the cosine of the first one times the sine of the second one to build our sine-wich. And just remember, if it's plus here, it's going to be plus here. If it's minus here, it's going to be minus there. All right. And then we'll move on to cosine, which is just a little more confusing, but it's not that bad. We're going to have our cosines together. So have cosine first of both plus, or actually it's going to be a minus plus of the sines of both angles. And just remember, cosines stay together. Spelling. All right, and once again, I just want to make it clear that if you have a plus in here, it's going to be minus for the identity. And you have a minus in here, it's going to be plus for the identity. So just remember that. All right, we're going to move on to the tan summation formula. Oh, and I just wanted to note, these are super important. You have to remember these. I would memorize them over and over again because these are used all the time and you'll need them in calculus. Anyway, moving on, we will find it for tangent. And this one's even more straightforward. Always remember that we know what tan is. Tan of any theta is equal to sine theta over cosine theta. So that means we can apply these principles, right? So we're going to get sine of alpha plus beta over cosine plus alpha of alpha plus beta. And yes, remember it tells us to start with the left-hand side, so I'm starting with the left-hand side. All right, so moving on, if we use our formulas that we just learned, we're going to get sine alpha cosine beta plus cosine alpha sine beta. And remember, on the bottom, we're going to use our cosine identity, so it's going to be cosine alpha cosine beta. And then remember, minus sine alpha sine beta. All right. And from here, we're just going to notice how we want all these tans, right? Like we see all these tangents in here. And we remember that tangent is sine theta over cosine theta, right? So we're probably going to need to divide some sort of cosine theta to make sure we have cosine thetas all on the bottom everywhere. And from here, we're going to multiply the top and the bottom by 1 over cosine alpha cosine beta, which is this one here, which is how we're going to get our 1. And if we expand this out, we're going to get sine alpha cosine beta over cosine alpha cosine beta. Notice how these will cancel. Plus cosine alpha sine beta over cosine alpha cosine beta. Notice how these will cancel. Over, if we divide this by itself, it's going to be 1, right? So we're going to get the 1 right off the bat. And then sine alpha sine beta over cosine alpha cosine beta. Notice how we have tangent alpha tangent beta. So if we continue, we're going to get tangent alpha plus tangent beta over 1 minus, and then we have our tangent alpha times tangent beta. And we can confirm that's equal to this. And obviously, we can use this exact same example to find it when it's negative on the inside. And notice how when it's negative on the inside, the top is positive. I mean, the top is negative, so these are matching. And then when it's negative on the inside, the bottom is positive, so these are not matching. So if you want to really generalize this, you can get tan alpha plus minus beta is equal to tan alpha plus minus tan beta over 1 minus plus tan alpha tan beta. So basically, the bottom will have a different sign than this, but the top will have the same sign. And I'll just write this in orange to make sure you remember. And yeah, so this is somewhat important to remember. These are somewhat important to remember. It's just nice because if you're using tan a lot, you can just skip to this instead of having to derive this on the test. So moving on, I'll let you guys do these because I don't want to waste my time on that. Let's move on to something more important, which is double angle identities. And these get used a lot. So if you really think about it, what is a double angle identity? It's just a sum, right? Because what's 2 theta? Isn't 2 theta just equal to theta plus theta? So we can use that here. Sine of theta plus theta, if we use our sine which is equal to sine theta cosine theta, right? First and second, plus sine theta cosine theta. Notice how they do the exact same thing. So this just becomes 2 sine theta cosine theta. All right, and that's important to remember. So keep that in the back of your head. Apply the same principle to cosine. And it's going to give us cosine of theta plus theta is equals to, have our cosines first, cosine theta minus sine theta sine theta. And this is going to give us cosine squared theta minus sine squared theta. And obviously, this is it. So it's telling us to find two other representations of cosine 2 theta using other identities. So I want to give you a moment to think about it if you haven't already. But remember the very first identity you learned, which was sine squared theta plus cosine squared theta equals 1, right? So if we have cosine 2 theta is equal to cosine squared theta minus sine squared theta, we can take some of these out, right? We can do some substituting. So we're going to solve for cosine squared theta first, which is equal to 1 minus sine squared theta. So we're going to plug that in. So 1 minus sine squared theta minus another sine squared theta means it's going to be 1 minus 2 sine squared theta, right? So this is one of the first two representations. Or we can go a different route, which is substituting out the sine squared theta for 1 minus cosine squared theta. And this is going to give cosine squared theta minus 1 minus cosine squared theta, right? Because we're taking out the sine. So this is going to give 2 theta cos is equal to 2 cosine squared theta minus 1, because this becomes a positive, right? Because you're using 2 negatives. So this is the other one that is pretty nice to remember. It's all just dependent on the situation and what you're trying to find and how you would implement and which one you want to choose. So for these are called the power reducing formulas. And I don't know a great way to do this. I don't think we never really proved it. We just learned this. So the one important takeaway you want to get from this is something called the half angle identity, which is really nice if you have half an angle, but that doesn't show up too often. But I'll just demonstrate how it works here. So from here, you just want to take the square root from both sides of the power reducing formula. And these aren't, like I said, these aren't the most important things to remember. But it looks like you can just prove it by moving this sine squared theta to this side. Yeah. So it should be pretty easy to prove. If you need me to prove it, I can, but I probably won't do it today. And anyway, moving on to taking the square root. And this becomes 1 plus cosine 2 theta over 2. All right. Notice how for cosine, the inside has a plus 1. And for sine, the inside has a minus. Just remember that. That will be helpful. So you can just think of it as like, since the inside is always a cosine for both of them, when it's with cosine, it likes to be positive, and it's with sine, it likes to be negative, because it's not happy when it's not with cosine. I don't know. That's just how I remember it. It's a little stupid, but it's kind of funny. And also notice how this theta is half of the 2 theta. So you can just kind of rewrite this if you use a quote-unquote new theta. So cosine of half theta is equal to plus or minus 1 plus cosine theta over 2. This is the official one. And you can do this the exact same way with sine theta. So sine theta over 2. And we're not doing anything mathematical here. We're just changing out the variables. So this inside variable just has to be half of that variable. And yeah, so memorize these two as well. And moving on, we want to use it for tangent. And the great thing about tangent is there are 3 different ways you can do this. Obviously, I don't want to go through all of that, but I will do it anyway because it looks like this is the last thing we need to prove, so that's great. All right, tan of half theta is equal to tan, remember, going back to the most basic definition, which is going to be sine theta, 1 sine half theta, or cosine half theta, which is equal to r plus or minus 1 minus cosine theta over 2, or plus or minus 1 minus 1 plus cosine theta over 2. And this is going to equal, if we do some canceling, 1 minus cosine theta over 1 plus cosine theta, if I'm not mistaken, with, yeah, the big plus or minus sign on the outside. So this is the first one you'd like to remember. This is the first version of it. And we can keep going. So if we have this, we have 1 minus cosine theta, right? And 1 plus cosine theta. We can multiply by the conjugate of either the top and bottom to get 2 different versions, 2 new versions of this identity. And if we multiply by the conjugate of the top, which is going to be this, and then 1 plus cosine theta, this is going to give us something that looks like this, which is equal to, if we do the conjugate thing on the top, it's going to be 1 plus cosine squared theta. It's actually no, minus, my bad. Minus cosine squared theta on the top, and it's over 1 plus cosine theta, just squared in general, on the bottom. And if you just remember from our Pythagorean identities, the top is equal to sine squared theta. So if we have sine squared theta here over 1 plus cosine theta squared, the whole square root thing cancels out, and we get sine theta over 1 plus cosine like this. So this is the other one you need to remember. And we'll do it one more time, but instead we'll multiply by the conjugate of the bottom this time. So 1 minus cosine, like this. And this is equal to mostly the same thing, except it's 1 minus cosine theta squared on top. And then we still have that 1 minus cosine squared theta, which is going to be equal to sine, and that will cancel out of the thing. It's become sine theta 1 minus and this is the other one you have to remember. So 1 minus cosine theta over sine theta is equivalent to sine theta over 1 plus cosine theta, which is also equivalent to the square root of 1 minus cosine theta over 1 plus cosine theta. And this is all equal to tangent of half an angle. And that's basically all the identities you will ever need to learn. Yeah, that's pretty much it. So thank you for watching. If you need more help, just let me know. But I hope this was of help to you, and have a nice time. And I hope this helps you get to a better grade or something.